Hi, and welcome to another edition of Calculus 3. Today we are going to continue our conversation about partial derivatives. Today is exclusively about practice problems related to this topic that's going to dominate pretty much everything from here onward. So let's go ahead and see uh, how we are going to deal with these type of problems. Uh, on this page, I've written some formulas that you are familiar with from Calculus 1. So the derivative of uh, an expression to some power. In this case, n is supposed to be a fixed number. An expression to a power, you remember that the derivative of that is the power times the expression to 1 less than the whole power times the derivative of the expression itself, and so on for the rest of the formulas you are familiar with. Exponential of an expression, the derivative is exponential of that expression times the derivative of the exponent, and so on. So in all these cases, the function was a function of one variable, and we were taking derivative with respect to that variable. Typically u is some kind of a substitution that is in terms of some variable, traditionally variable x, and here u prime represents derivative with respect to that variable. Now in calculus 3 we have functions of multiple variables, and when we want to take a derivative we have to specify with respect to which one of them. So there could be x, y, z, and so on. So suppose I have a function again. Now this expression u could be a function of many different variables, still raised to some exponent, and suppose I want to differentiate with respect to x. How would it go? Essentially almost identical to what you had before, except that you have to specify your u prime is with respect to whatever variable you are interested in. So instead of n u to power of n minus 1 u prime, we have n u to power of n minus 1 times u sub x. So you see in all of these examples, instead of u prime, I have u sub x. Of course, if you wanted to take a derivative with respect to y, z, and so on, this would be derivative with respect to that new variable that you have in mind. Let's go ahead and practice this in the context of a few examples. So let's write, say, example 1. So let's suppose z is equal to, say, 2x plus 3y to power of, say, 10. And I want to figure out what is z with respect to x. So now I think about this base as an expression in terms of x and y. So this is u to power of 10. The derivative of that, if I'm taking derivative of this thing with respect to x, by the rules that we learned just up there, it's 10 u to power of 9 and then u sub x. What is u? Well, u is that our substitution that we are using, 2x plus 3y, and u sub x would be just derivative of this thing with respect to x, which is just 2. So our final answer, u sub x becomes 2 times this becomes 20. U to power of 9, u is 2x plus 3y to power of 9. So z sub x would be the exponent, which is 10. Derivative of the base with respect to x, that is 2, times the base, which is 2x plus 3y to power of 9. So 10 times 2 will be our 20 here. Let's practice this thing with respect to y as well. Let's see, you can quickly come up with what the derivative is before I write it. So how about just taking a second off this page and coming back on. So what do you think is the answer? So we have 10. Derivative of the base with respect to y will be 3, so that's going to be 30. and the rest is the same, 2x plus 3y to power of 9. Let's go ahead and do several other examples. Suppose I have example 2. Suppose I have z is equal to, say, sine of xy. So what I want to do is z with respect to x, that's my expression, or the interior function. What's the derivative of this with respect to x? Well, the derivative of that is y. Derivative of a sine will be cosine of whatever the input was before. So as simple as that, we are done. So you want to go ahead, perhaps practice z sub y for yourself. Let's go to another example. Suppose I have say z is equal to cosine of 5x minus 7y. I want to find z sub x. Derivative of cosine will be minus sine, so I can write that minus sine of whatever the expression was, 5x minus 7y. Now the derivative of the interior function is just that you're taking derivative with respect to a specific variable with respect to 5, but derivative of that with respect to 5 is just 5. Excuse me, derivative of this with respect to x is 5. How about z with respect to y? Well, a minus 7 is going to come out, and I have a minus before, so it becomes 7 sine of 5x minus 7y. Let's do another example. Say I have z, let's make it a bit more complicated. Say x times y over square root of 2x squared plus 3y squared. So we are making the problem gradually more crowded. Let's just go after z sub x, and I leave the other one to you. Rules of derivatives same as before. That is, if you have numerator or denominator and you want to differentiate with respect to, well, now it's with respect to, say, x. Just exactly same as rule of quotient you had before. Derivative of numerator times denominator minus numerator times derivative of denominator over denominator squared. So let's specify derivative of, so I write what I want to differentiate, xy, I want to differentiate that with respect to x. Then I have to multiply with the denominator, which is 2x squared plus 3y squared, minus numerator as it is, times the derivative of denominator. So for a moment I write down what the denominator is and indicate what I want to do with it, which is take a derivative of this thing with respect to x over denominator, whatever it was, 2x squared plus 3y squared, and this whole thing has to be squared. Now some parts are going to be immediate, some parts going to take a while, but we just patiently go through all the steps. Derivative of xy with respect to x. Okay, we don't want to make a mistake here. Derivative of this, if you want to think about it, y is supposed to a constant. It's held as a constant. For example, y could have been a 5 or a 7 or 11 or a pi or anything like that. If I had the derivative of an expression x times some constant with respect to x, just that constant survives. So it's y is the derivative of that. The other expression stays as it is, 2x squared plus 3y squared, minus numerator, which was xy, we leave it alone. I want to take a derivative of this radical. Maybe it's a good idea to put a particular example here. If I had a square root of u, well, that would be u to power of 1/2. The derivative of that is 1/2 u to power of minus 1 half times the derivative u prime. Well, to clean this up, we can write this thing as u prime over 2 radical u. Is that right? So the derivative of radical u, cleaned up version, is u prime over 2 radical u. So in this case, it's going to be u sub x over 2 radical u. And so on. You can make specific rules for particular exponents and such. So derivative of this expression with respect to x would be the derivative of the radicand. So let me write it here. The radicand is 2x squared plus 3y squared. That has to be taken with respect to x divided by twice the radical itself. 2 radical 2x squared plus 3y squared, and denominator, just when you square it, becomes 2x squared plus 3y squared. Well, we have almost there. We have to take one more step, zx. This is y times this radical. Minus xy, that stays there. Derivative of this radicand with respect to x, well, that's going to be derivative of 2x squared. Derivative of y is going to be 0. The derivative is going to be just 4x. So I have 4x over 2 radical 2x squared plus 3y squared divided by 2x squared plus 3y squared. We are done with differentiation, but in a typical application of these problems, you need to clean up this expression to be able to do various things with it later on. You remember, our job isn't just take a derivative. We typically use it to find high points, low points, and a variety of properties. And to achieve those goals, we need a cleaned up formulas. This is messy as it is. We have to clean it up. So here we get a little bit of a breather that 4 and 2 simplify. It becomes a 2 here. I take this radical, multiply the numerator and denominator with it to clean it up. When I multiply the numerator with it, that radical times this radical, the radical goes away. So I'll have y times 2x squared plus 3y squared. When I multiply this expression with this radical, the radical goes away, and I'll have 2x times xy becomes 2x squared y. Is that right? 2x times xy becomes 2x squared y. And I have to multiply the denominator with that radical as well, or take a common denominator. If you're comfortable doing this some other way, just do it that way. So this is power 1, this is power 1 half, so overall becomes power 3 halves. It so happens that in this case 2x squared y and 2x squared y cancel out, and our expression happens to be some cleaned up version that looks like this. You agree with me that this expression is a ton simpler than that one. So when we say simplify, that's always an open-ended question. What is exactly to be done? It all changes from problem to problem, and you have to just try to clean up your expression. Okay, let's do some other examples. Say something with a logarithm. So this was problem 4. So another example, problem 5. Say z is equal to logarithm of 2x squared plus 5y cubed. Let's do z with respect to y. Derivative of logarithm, you remember, was u prime over u. So now it becomes u sub y with respect to u, meaning the interior function, whatever it is, you have to differentiate it with respect to y and then divide by that the interior function. So here we indicated what we are supposed to do, and then next stage we actually do it. Well, derivative of this with respect to y, we have practiced that, 15y squared over 2x squared plus 5y cubed. So that was another example. Let's do another problem 6. Let's do a function of 3 variables. Say I have x, y over x plus y plus, say, z. I want to differentiate. I can ask for derivative with respect to x, y, z, or mixed derivatives and so on. Let's do w with respect to z. So x and y, z are now independent variables. Y depends on all 3 of these things and is given by this particular formula. I want to take a derivative with respect to z. So derivative of numerator with respect to z, there's no z here, so its derivative is going to be 0 times denominator, so that's going to be 0, minus derivative of denominator with respect to z is just 1, times numerator, so that's going to be x y divided by denominator squared, x plus y plus z, and then that is squared. That's it. So we clean it up. Typically don't write a 0, and minus typically comes in front to make the expression look tad cleaned up. So that's as simple as that. We are done with that problem. Let's do what else is it that we haven't done. Let's do say z is equal to exponential of say minus x squared plus xy plus y squared, and say we are asking for z sub x. You remember exponential of u has a derivative, perhaps one of the cleanest formulas. So it's going to be the derivative of exponent. It's just that instead of prime we have with respect to some variable. So if I'm taking derivative of this thing with respect to x, I have a minus derivative of x squared is 2x, derivative of xy with respect to x, what is that? That is of course y. You want to make sure you don't make a mistake here. Exponential of minus whatever we had before, and as soon as we are done with that, we are essentially all done. Let's do one last one of these things. Say problem 8. Here z is equal to say exponential of x tangent of y. When your variables are separated like this, the derivatives take on a simple form. If we want a derivative with respect to x, since y is constant, tangent of y is a constant, this whole thing is just a constant. Derivative of e to the x is just e to the x, and this is a constant multiple, so the derivative of this function is exactly itself. How about if we were asking for z with respect to y? Well, exponential of x would have been a constant now, so that would be exponential of x. Tangent of y will be secant square of y with respect to derivative of tangent of y with respect to y is secant square of y. So this is a variety of problems you might see here and there. And uh, for those of you headed toward more advanced mathematics, we have a course called partial differential equation that comes after the course on ordinary differential equation. So we have after this class, typically students take something called ODEs, that is ordinary. There's nothing ordinary about it, but that's what's called ordinary differential equations. So pretty much all engineers are asked to take that class. Of course, math students also take that class. Physics students, no doubt, they're going to take that class. There is another class after that, typically optional, but strongly advised to take that. That's called partial differential equations. It could be a senior level class or something. After you have taken this, you take that one. So as you can suspect, partial differential equations is built on a lot of equations that have partial derivatives in them. These are some of the very famous, very important equations of mathematical physics. Wave equation, heat equation, a large variety of equation in physics or engineering and mathematics are these types. So we have the famous wave equation. An example of that would be UTT is equal to UXX. So u is a function of t and x. Its second derivative with respect to time is equal to second derivative with respect to position. That happens to capture simplest type of waves. Like if you have a slinky and you're playing with that slinky with the waves going back and forth in it, it has a wave equation similar to this. If you have a guitar string, you pluck it, it starts to vibrate. At the simplest level, the equation that guides the movement of that guitar string is this type of a wave equation. We have something else called the heat equation. Heat equation governs how heat spreads inside the body of an object, typically a metal object. Heat could be entering from one end, spreading through the medium, and you want to know what's the temperature at any location at any time. Simplest form of this equation is u sub t is equal to u sub xx. So on the left side we have a single derivative with respect to t. There's a word of difference between these two, simply due to the fact that these derivatives, one of them is double derivative and the other one is single derivative. And then you come across many others depending on the area of your study. We might see some of that ourselves in this class. Laplace equation. Laplace equation, you see it in electromagnetism, you see it in mathematics, you are going to see it in your complex variable class, and so on. So it could look like the following: u sub x x plus u sub y y equal to 0. It comes up in the study of perfect flows, also properties of potential function in physics, and so on. So as you become familiar in these topics in your advanced engineering or physics or mathematics classes, these type of equations also come up. So the common characteristic of all of these things is that you're looking for an unknown function whose partial derivatives have a certain relationship with each other. Now, some of the homework exercises in this section is going to ask you to verify that certain solutions satisfy one or another of these equations. Let's, for example, pick the following. just problem 99 in your textbook. It says, let's look at the following. Z is equal to sine of x minus ct. Okay, so c is some constant, so c a constant, and you're asked to show that this function satisfies second partial of z with respect to t is equal to c squared times second partial of z with respect to x. Okay, this is a full style of writing this kind of equation. When we abbreviate it quite a bit, we write it this style, but in the Leibniz notation we spell it out. I'm taking second derivative with respect to t, second derivative with respect to x, and c is a constant. What's the meaning of that constant? When you study wave equations, well, a wave spreads at a certain speed, and when you want to take into account that speed in your equation, it shows up here. So when we put a c squared here, that indicates the speed of the wave. Mathematical version, c is taken to be 1, but in the physical version you typically spell it out. Well, what is the derivative of this thing with respect to t? So let's do step by step. Instead of this notation, let me use the more abbreviated notation. So this is same as z, partial of z with respect to t. Well, I want to take a derivative of this thing with respect to t. We said take this interior expression, consider it like u. You have a sine of u. Want to take a derivative of that. How do you take a derivative? Well, first derivative of sine is cosine. So it's going to be cosine of u, which is in this case cosine of x minus ct. Then you have to multiply by u prime. Well, instead of u prime, you think about u with respect to t. This is an expression, interior expression. You want to take a derivative of it with respect to t. Well, derivative of this thing with respect to t is going to be just minus c. Next level up, we are taking partial, second partial, or in abbreviated notation, z sub tt. We have to take a derivative of this thing one more time. First of all, derivative of cosine becomes minus sine. So I'll write minus sine of that expression to make sure my negatives do not collide with each other. I had a minus c before here, and derivative of this expression with respect to time a second time around is another minus c. So I have three minuses, and overall it becomes minus c squared sine of x minus ct. So I have calculated left hand side of this equation. I want to show that this function satisfies that equation. Well, I have to calculate this derivative, and show that those two become equal to each other. So I have still more derivatives to take to calculate my right hand side. So I say, what is partial of z with respect to x, or in shorthand notation z sub x? Well, derivative of this thing with respect to x, what's that going to be? The derivative of x with respect to x is just 1. It becomes cosine of x minus ct. How about second derivative? Second partial of z with respect to x, or zxx. I have to take a derivative of this thing again with respect to x. Derivative of cosine is minus sine. Derivative of the interior function with respect to x is just 1, so I just have a 1 here, minus sine of x minus ct. What is it that this equation asks of you to show? It's asking you to show that this whole thing is equal to this expression times the c squared. Derivative of z with respect to t, second derivative with respect to t, is equal to, so here you are right, minus c squared sine of x minus ct. This is the left hand side of this equation. We want to show it is equal to a c squared times this second derivative, which is minus sine of x minus ct. So if I simply remove these parentheses and move the minus in front, you see that the two are actually equal to each other. Well, this is mathematical mechanics of showing the derivatives work on two sides. How does this relate to a wave? Well, it's going to be a bit more involved to see that this is a kind of a wave that moves to the right hand side at the speed of c and such, and that is going to be an introductory lecture in partial differential equation, which hopefully you'll take in next year. Okay, so as we said, the purpose of this discussion here was that partial derivatives are going to be with us for the remainder of this semester. So it's a bread and butter of all sorts of calculations that you do. You must be able to do it precisely and quickly to get through just about any exercise you are going to have from now on. So try to do as many exercises as you can, and there may be just 5 or 10 of them on your homework, but attempt to open your book and do another dozen or two to become comfortable with it. Okay, until next lecture, which is going to be on differentials. Good luck and God